Okay, so the football problem. What number is this? This is number 2? I don't know. I don't know his numbering system. Anyway, we did talk about, well, I did a whole separate video on how we're going to integrate the to find the volume. I mentioned I'm used to using Z first, but it didn't work out. It turned into a train wreck. And so the easier way, which I've never actually done before, was to actually do it with respect to R first. Oh, first of all, we're doing it in cylindrical. This is obviously a circular around an axis, so it definitely lends itself to cylindrical. This is your x, y, z plane, but if we are going to cylindrical, your thetas are R and theta are basically the same as polar. They're all in the x, y plane, so your R is just a distance in the xy plane to a point, and even if it's a point above the xy plane, like a point somewhere in here, let's say, we would find the projection onto the xy plane, and then that distance from the origin in the xy plane will be your R, and then your theta will be measured, that angle there, from counterclockwise from the positive x-axis as you do in trig. So that point right there is about here, and your radius is there, and your theta is there. Okay, but anyway, which means that the side view, looking at the z-axis and the xy planes here, we can think of it as an r plane. That point there would be about here, or sorry, it'd be here, and the projection would be on there. Okay. Anyway, what we're going to do is we're going to integrate. I'm going to set up my integral first, and then we'll talk about the momentum thing. I'm going to review what I already talked about. Triple integral. My usual way of doing z first did not work because I'd have to figure out the upper curve and the lower curve. They are separate. I have to split that up and do it creatively, and it did not work out cleanly. So instead, I'm going to be doing with respect to r first. And that means r is going to come first. Cylindrical has a Jacobian of r, just like polar. It's 3 dimensions, but the z dimension doesn't add anything to the Jacobian, so it's still the same Jacobian as polar. I'm going to do r first. Then probably, I think that z and theta are interchangeable, and neither way is better than the other, but I'll do theta first and then z, for it's more intuitive for me. So when I want to think about what my bounds are for r, I have to imagine theta and z just being some constant, which means I'm going to pick an arbitrary one. And so an arbitrary r would be like something like that. My arbitrary theta would be some angle. Wait, sorry, not arbitrary r. Arbitrary z. So arbitrary z, I'm going to say right here. My arbitrary theta could be pointing out in any direction. I'm going to have it coming right at us, so it'll pop out of there right there. And that's our slice. And we have to think about that going from the axis, which is r is equal to 0, and then emanating that way like that, and piercing right there at the, oh, I shouldn't do it over here, because it's not the circle, it's my footprint. Ignore that for now. Let's say I'm doing it over here. I pick my arbitrary z right there. I'm going to pick my arbitrary theta, pointing out directly, and so that's going to come out like that. Oops. Let me clean this up. So this curve is r is equal to sine of z. He didn't give that to you. He gave you square root of x squared plus y squared is equal to sine of z, which means that when we convert it to r, square root of x squared plus y squared is equal to r. Anyway, to set up my bounds of integration, I'm going to imagine picking an arbitrary z, and then an arbitrary direction in which to slice through to pierce the football. And now I have to think of my outer curve and my inner curve. My outer curve is this, r is equal to sine theta. So it's my outer curve. And my inner curve is right here. It's the axis, that's r is equal to 1. Sorry, r is equal to 0. What am I talking about? R is equal to 0. Okay, and that'll be that little piece coming out from the center out. little worm burrowing out of a fruit. And then next I'm going to do theta. I got to think about all the thetas that I need. I want to just basically do all the different thetas along that, the same z, but just do that slice. So now I'm doing an entire slice right there in the middle by letting theta range from 0 to 2 pi. And then the last step is I want to integrate all those slices starting from z goes to 0 all the way to z is equal to pi. Okay, and the last time I did this, I said if I just wanted to verify his volume, so I said we're going to just integrate 1 there. You have the Jacobian, so it ended up being an R integrand, but just integrating the function 1 is going to give you the volume of that solid. And it worked out a lot better than if I had done z first, which is what I'm used to doing. Now we're going to do a moment of inertia, which means we are going to have an integrand, which we'll talk about. And I'm going to mention that that means we have a new integrand, and it's possible that this particular setup is not going to work as well, and we should go back to z first because it'll work better with a different integrand. I don't think it's going to be that way. I think we're still going to stick with this, but be aware, different integrands will work better or worse with different orders of integration. So you have to adapt to not just your shape, but also what you're trying to integrate. That does factor into which one's going to be easier for you. But I'm pretty sure it's going to be the easier way in both situations. Anyway, let's talk about moment of inertia. I don't know how they gave you. In physics, they give you just a bunch of shapes. They'll say like a solid disk will have moment of inertia. Ooh, they use I, right? Capital I? Capital I, and they'll give you a formula for it. And then they'll say a sphere spinning around the axis like the Earth. That'll have a moment of inertia, something like that. And they'll just give you formulas a lot of times, but it comes from, if you wanted to derive these formulas, you could do what we're going to be doing now, which is using an integral. And I think all of these generic basic shapes that they teach you in physics and teach you the formulas for moment of inertia are actually pretty easy integrals that you could do. I think we've got a harder one than the ones to derive these. But the main one that we need to use from physics is a point mass. So the idea is we're going to let it spin around the z-axis, simply because this is what we're doing here. Yeah, it's got a little arrow saying our axis of rotation is the z-axis. And we want to look at a little point mass, which means a little voxel of volume. There. Actually, I want to put it further away. And if I project it, let's say it's floating right there. That's its projection onto the xy plane. Okay. And since it's spinning around the z, that moment of inertia of that single point is given by the mass of it. I don't know. In the formula I saw in Wikipedia, they're saying it's a distance from your axis, a perpendicular distance, and you have a mass there. And it's going to be the mass times your distance squared is going to be your moment of inertia. I'm going to rewrite that in terms of the variables that we're going to be using. That's the idea. Just the radius squared from the axis of rotation times its mass. Going to what we're going to be doing. That distance is the radius, literally the r in our what do you call it? Wait, what just happened? I didn't need a shadow. Okay, I was thinking, I didn't do the shadow. I don't need it if I do it that way. I needed it if I did it with z first, so that's not necessary. Anyway, let me backtrack. What was I doing? The radius is literally the radius that we're using in our integral here, the r in cylindrical coordinates. The mass we got to talk about. And we're going to be using the fact that he gave us density. Don't worry about the fact that he doesn't want density in his final answer. We'll worry about that after we do our integral. But your mass of this is a density times a volume. That's your constant. Unfortunately, he gives you constant density. Sometimes density can be given as a function where it's denser in the middle and not as dense on the outside, or vice versa, or denser on the bottom and less dense on the top, where it's wobbly football. But a lot of times it'll give you constant density, so delta is a constant density, and your mass is going to be the density times the volume of that little piece, that little box of mass. And so the mass of this little piece is going to be the constant density times a little dV, the dV being that little volume that's going to come out, that's representing that dr d theta dz when we rewrite it as an integral. Okay, anyway, so the moment of inertia of this point mass is given by r times delta dV. And then now what I want to do is I want to integrate all those little pieces. That's just one of many pieces that makes up the football. So now I want to do all the pieces, all of them, all over the place. There's billions of these. Okay, which means that what I'm trying to do is, and I'm going to write it over here, I'm trying to integrate over the volume, little dV's, that integral. I don't need that big a thing. dV r times delta. Okay, so that's what I want to do over the volume of the solid, which you call it W. I didn't label it here, but we're calling it W. So he wants you to integration is basically adding up all the pieces. Well, I want to add up all the little moments of inertia of all the little pieces that makes up the solid W. So that's the generic form of what we're doing. It's regular multiplication. And then I would need to spend some time thinking about how I'm going to break down this volume. How am I going to integrate over a three-dimensional solid? And since I've already worked out that the best way approach is to do cylindrical, I'm going to throw in a Jacobian. I would next think about the order that I want to do it in. And here I want to do dr d theta dz. I think about my boundaries, and my boundaries I've already worked out is 0 sine of theta, 0 to 2 pi for theta, 0 to pi for z. And that's it. That's what I want to do. I will again worry about getting rid of the delta later. He does give you some new variables, mass and the total volume and whatnot. That'll help you to rewrite it in terms of capital M without delta. That's to be done later. Let's just do this. Let's space this out weird. Okay. Let's see. My delta can come out. And I'm going to integrate r squared. Antiderivative, I'm doing with respect to r first. I'm not going to rewrite it, but it's r squared I'm integrating. It's going to be 1/3 r cubed. I'm going to evaluate that. R goes from 0 to sine cubed. No, sorry, sine theta, but I'm anticipating it's going to be cubed eventually. And then I'll do d theta, then dz. Okay. My next one task to do is integrate sine cubed. I'm going to rewrite it as sine. No, what do I want to do here? Whenever it's an odd power, you want to split off. You want to use an identity for squares, all the squares, and split off just one of the odd number trig functions. Then you can do substitution. That's going back a little bit. So then I can do u is equal to cosine d will equal negative sine theta du. Sorry, d theta. My boundaries will be, that's theta boundaries. When theta is 0, I have 1. When cosine of theta, cosine of 2 pi is also 1. What? I gotta think this through. Bounds. Alright, I gotta pause this and figure this out. I just figured it out. I just said it was r squared times your mass, and I forgot to square it. So once again, let me backtrack. So the moment of inertia is given by the radius squared, the distance squared, times your mass. Let me write it out. Which means it's radius squared times delta with a dv. Okay, so I just missed a squared, which means my integrand is delta r squared. That's before I decide I'm going to do cylindrical. That's me just setting up a generic integrating over a volume of a solid. Then I need to take that integrand and throw in the Jacobian. So it's an extra r squared coming from there, an extra r as a Jacobian used for cylindrical coordinates. That's going to change me to integrating, so the delta can still come out. I'm going to be integrating r cubed. I'm going to get 1/4 r to the 4th. And plugging in sine theta for r and 0 for r will give me that. Okay. Holy shit. Okay. Odd powers of trig functions works out nicely with a substitution by using identities, a Pythagorean identity, and splitting off just one of the other trig function, and you can do substitution and it comes out clean. If it's even powers, ooh boy. I don't think I'm going to do this. I think I'm going to pause this and go on my computer and do it. But it is, you're treating it as sine squared theta times sine squared theta. You're splitting it up into squares, as many squares as you need, and using the identity, the half angle identity, into all of them. I worked it out. It's going to be 1/2 minus 1/2 cosine of 2 theta times another one of those. I'm not going to write my limits of integration until I'm ready to do this. I got a lot of work to do to get there. I'm going to have a clean 1/4. I'm going to have 1/4. It'd be minus 1/2 cosine 2 theta. When I combine my inner and outer terms, it'll be negative 1/4 of those. Minus another 1/4 will be minus 1/2. And then I will have plus 1/4 cosine squared 2 theta. That's doable. That's just a constant. So your antiderivative is going to be, I got d of z here as well, but I'm not focusing on. Just a constant, so it'll just be, and I'm integrating with respect to theta next. It'll be 1/4 theta. That's pretty easy. It's going to be, technically I got to worry about that too, but no big deal. That's another square. So, oh my god, this is how it works when you have 4th or 6th powers of a trig function. Sine or cosine is you're going to have to do that, FOIL it out. Any other squares, you got to do the identity on that again. That's going to be 1/4 times 1/2 plus, right? That's going to be 1/2 cosine of double the angle, and that angle is 2 theta, so now it's going to be 4 theta. So each time you apply it, you're doubling the angle. Okay. It's going to be 1/8 plus 2/8, 3/8. Okay, so just old trig stuff. I'm going to erase. I don't need this. This is just my explanation. You get the idea. You're just doing a little piece and then figuring out what that inertia of this at a little piece, and then integrating, meaning summing up all those inertias of all the pieces that make up the football. I'm gonna go way over here. Sorry, I'm all over the place. And it's just mostly that crap right there. I was tempted to just skip it, but some of you might need it. Alright, let me do this. I'm gonna have 3/8 theta minus antiderivative sine, so it's going to be 1/4 sine 2 theta, and then I'm going to have a 4, so it's going to be plus 1/32 sine of 4 theta, and I'm evaluating that from 0, and let me throw in my things now. Where'd it go? It was 0 to 2 pi for theta. And it was 0 to pi for z. That's to be done later. Okay. Alright. 2 pi and then 0, so it's going to be 3 pi over 4. 2 pi is going to be 4 pi, 0 is going to be 0. That's gone. That's gone too. Is that it? Alright. Yeah, because it's all just sines of multiples of 2 pi. I think I got 3 pi over 4. I'm not done. Doing with respect to z last. That's a delta not neat. I'm going to have 3 pi over, I can pull that out, so what I got is now 3 delta pi over 16, which is going to be z, pi minus 0 is pi, so I got an extra pi. 3 delta pi squared over 16. I believe that's my moment of inertia. I do have the issue of now I have to rewrite it without a delta, but let me pause it and just make sure I did this correctly and check it on my computer, and then I'll continue from there. So far, this is our answer. It's not the form he wants it in, but that is a moment of inertia in terms of the constant delta, if I've done it correctly. Let's see. Okay, I'm good. That is correct. That's not what he wants, so now let me see what he wants. I'm going to erase all this. This is all just busy work with me having to deal with a sine to the 4th. So it got pretty ugly. I mean, not undoable, and I still feel like that's going to be a better way than doing a different order of integration. Although you could test it out and see if maybe this integram makes it easier to do it a different order. Now I just have to convert that answer, because that is my answer, but he wants no delta. So I just need to use physics properties. Delta, well, so your mass, he gave you the formula, but basically your mass of an object is equal to the density if it's constant times the volume. That's your basic physics concept of density, or what he wrote, which is density is just your total volume divided by, no, your total mass divided by your total volume. Is that right? Pounds per square, or per cubic inch or something. Yeah, okay. Mass divided by volume. Okay. The mass of W is M, capital M. He's leaving that there. The volume of this particular football he gave you, which we did earlier, that's pi squared over 2. And that's your delta. And you just want to incorporate that into that, and you're done. Yeah, so I'm almost done. Equals 3 times my, I should clean this up, sorry. It's going to be 2m over pi squared when you do the flippy thing. Is that right? Mass over volume, yeah, okay. And then right here, my delta, my density is 2m over pi squared times the pi squared from here, divide by the 16 from here. Pi squares cancel. I'm going to get 6m over 16. 2 is going to cancel, so I'm going to get 3m over 8. And that's it. I wouldn't worry about that conversion to capital M until you get this in terms of delta, because usually when you do inertia and you're given a solid of constant delta, they usually like you to give your moment of inertia in terms of the density. He just had a weird ending requirement, which is he doesn't want the delta, he wants it in terms of the total mass. Which I guess is good, because if you have to actually have a football, you can't really find the density directly, but you can just put it on scale and get the mass. So yeah, maybe it's more practical. Anyway, that's it. I'm done.